Hello friends, my name is Sarnath. In this video, I'll be talking about Gaussian processes. What is a Gaussian process? A Gaussian process is a non-parametric technique that can be used for solving regression or classification tasks. It is primarily an interpolation technique. It shines when the number of data points that you have is somewhat less, so that the conventional methods do not give you a great answer, right? And the reason why it shines is the output of a GP is always a probability distribution. For example, if you take a regression example, the output is usually a continuous variable, right? Just a point prediction. That is what most analytical methods will give you. In case of Gaussian process, that output would be a probability distribution. And if the variance of the probability distribution is high, then you can know that the point at which you are seeking an inference is far away from the training data set. Directly it will give away, right? That is the beauty. And this is a part one of a two-part video. So in the first part, I'm going to talk about the theoretical understanding and the perspective you need to have and develop when dealing with Gaussian processes. This will be extremely useful to understand Gaussian processes. In part two, I'll take you over through a Jupyter notebook, which will start from basics like probability distribution, what is a joint probability distribution, what is conditioning on a particular variable, particular dimension, what is marginalization, all the way until solving a regression problem using Gaussian processes without using any library, just hand coding using the analytical formulas, right? So without much ado, let's jump into the video. What you see here is the traditional view of what a function is. A function is a mapping from a domain to a range. It could be one-to-one or many-to-one, right? But it can never be one-to-many. It can never be one-to-many, right? It can be one-to-one or many-to-one. That is the traditional view of the function. Now, if I invert this view and then look at this figure here, this is again a mapping from domain to range. Nothing much has changed except for the orientation, right? And in this view, you can see that the value of the function can be seen as a vector, right? This entire value can be seen as a vector, right? There are so many values put together, and so we can see them as a vector of values, and that makes these domain points as the dimension of the vector, right? Now we can look at these domain points, each one of those domain points, as a dimension of the vector, and the value is the vector. The values of these dimensions form the vector, right? So in this case, what happens if the function is defined on infinite number of points? For example, the domain is the set of all real numbers, which means that it's defined for each and every point in real numbers, so it's just infinite stuff, right? So in such a case, that would be an infinitely long vector, right? A function can be seen as an infinitely long vector, right? And in this case, I repeat this point one more time because it is important. Each one of the domain point becomes a dimension of the vector. Each one of the domain point. For example, if we consider a regression as a function, a regression is nothing but you have a descent matrix. For each row of the descent matrix, there is a target value of that variable. The target variable is assigned, right? So the target variable value is actually the function value, and the row in the descent matrix, which itself is a vector, it is the domain point, right? And if we try to view this function as a vector, then each one of those rows in the descent matrix will become a dimension, right? So this is a clarity that you need when you read Gaussian process, right? And before we move on, I think we should take a look at multivariate probability distribution. I know I'm suddenly jumping around. Just hear me out. You'll understand the connection. What you see here is a two-dimensional probability distribution, right? And if you random sample this two-dimensional probability distribution, you will get a random 2D vector. Every time you sample it, you will get a random 2D vector, right? Now, we just said the function is an infinitely long vector. If I have to sample functions from a probability distribution, what kind of probability distribution it has to be? It has to be an infinite dimensional probability distribution, correct? So Functions can be seen as random samples from infinite dimensional probability distribution or any kind of distribution as long as it assigns a non-zero probability to its participating domains, right? On all the dimensions, there should be a non-zero probability, right? Once we have that, we have an infinite dimensional probability distribution. You do a random sample, you get a function. Now, what happened to the domain, right? It looks we were talking about mapping from domain to range. Suddenly, we are talking about probability distributions. What is the connection, right? So, when I talked about vector, I made an important point saying that each of those domain point becomes a dimension of the vector, right? So, when you do a random sample of a function from a infinite dimensional probability distribution, right? The domain points dictate the covariance matrix of the probability distribution. Any kind of multivariate probability distribution is defined by two things. One is the mean, which can be assumed to be zero without losing generality, and the covariance matrix that basically tells how the different dimensions are related to one another, right? So if the covariance matrix is an identity matrix, then every dimension is independent of the other, which means that the value taken by the function in one dimension does not affect, does not constrain the values taken by the function for the other dimensions, right? They're completely independent, right? But if there is a covariance, then there is an interaction between those dimensions, right? So the connection now is that in the traditional view of the function, we have a mapping from domain to range, and a domain has a lot of points. If we can construct a covariance matrix that basically tells how each domain point is related to each other domain point, right? So if we come up with some mapping like that, then we can build a covariance matrix, right? And if I sample that distribution with that covariance matrix, then I will get a family of functions, and this family of functions will be very close to the actual function that we have seen, right? So we took a traditional function and then we have just converted into a family of functions by mapping the domain points into a covariance matrix and calling it as the characteristic covariance matrix of a probability distribution, and the family of functions that are arising from this distribution, right? That is how we are connecting the dots, right? I hope this was interesting to you. At least this view of functions is fundamental to understand what a Gaussian process is. So for that, now without losing generality, we can say that this infinite dimensional probability distribution is a Gaussian distribution. Why Gaussian? Gaussian has two spectacular properties. Gaussians are closed under marginalization. Gaussians are closed under conditioning. Let's first take up marginalization. What does it mean by Gaussians are closed under marginalization? If we take a multivariate probability distribution and then we marginalize it to one dimension, right? And that one dimensional distribution will be Gaussian. If we take a multivariate probability distribution and then which is a Gaussian distribution, and then if you marginalize it to two dimensions, those two dimensions will form a joint probability distribution, which again is Gaussian, right? So this applies to any k dimensions. You can just take an infinite dimensional Gaussian distribution. If you marginalize it to k dimensions, then those k dimensions will form a joint Gaussian. Okay, to be more clear, consider this as a 10-dimensional distribution, right? This is the normal distribution, 10-dimensional normal distribution, where x is 5 dimensions, y is 5 dimensions, right? So together they form a 10-dimensional vector, and this is the normal distribution. This is your mean, and this is your covariance matrix, right? A represents the covariance of x with itself. C is the covariance of x with y. C transposes y with x. B is y with y. If we take such a multivariate Gaussian normal distribution and marginalize it on x, the resulting distribution is this. You see that x is a normal distribution coming with mu x and A as the covariance matrix. As you can see, none of this depends on y, mu y, C or B. It's just independent. It doesn't depend on y at all. So which means that even if y is infinity, we don't care. We can just marginalize it, and we can simply construct a domain. We can simply construct a a probability distribution with x alone, right? X, mu x, and a. As simple as that. We don't need to worry about what the infinitely many other dimensions are and so on, right? This is property number one. And property number two says that the conditional distributions is, again, we get a Gaussian. What a conditional distribution means is that, let's say in this 10-dimensional distribution, if I specify the values of 5, let's say that I specify 5 values of for x as 1, 5, 10, 3, -2, then the distribution of y given given these values for x is again a Gaussian distribution. There's a formula for it. Actually, this is the formula, that this one that you say. If this one basically says what's the conditional probability of x given y, then it's a normal distribution. This becomes the mean, and this becomes the covariance matrix, right? And ultimately what matters is that this is a Gaussian distribution and we have an analytical formula for tackling it, right? Let's go and look at how do we apply this how do we apply this knowledge to a finite level. At a finite level, we have a data set in hand which is finite. For example, if that is a regression problem, we have a design matrix where each row represents the value of various features for that regression problem. And then we have a target variable whose value is a continuous variable, right? So that is what a regression problem looks like, right? Now, if we take, in the regression problem, this design matrix can be seen as your domain points, and the value of the function, which is the target variable, can be seen as this range of that function. Now, since it is a finite data set, we can say that this finite number of data points are actually coming from an infinite dimensional function, infinite dimensional vector. We are only looking at a subset of that vector. We are not looking at all the dimensions of the vector, right? Then we know that if that infinite dimensional vector is coming from an infinite dimensional distribution, if you marginalize it to only the dimensions that we are seeing in hand at the moment, then they can be seen as coming from a Gaussian distribution built on those finite dimensions alone. We don't have to worry about any of those infinite dimensions, right? So which means that we have got a finite set of domain points which can be converted to a covariance matrix, right? A symmetric covariance matrix we can convert, and then we can say that this function that we see, the finite values of this function actually came from the finite values of the function that we are seeing is that just a random sample from a probability distribution which we can construct, right? That's the whole idea. So you can take that finite data set and construct a normal distribution out of it, and then say that this function came from this normal distribution. We can say like that. And how do we apply conditional for this? Conditional for this, again, we can say that if x is actually the set of points for which we know the domain, which is our descent matrix, we also know x, value of x also we know, right? That is the target variable, that is our training set, right? Now we seek the values of y for a new set of domain points. So we specify a new set of domain points, we want to know y, right? Now, since we know all the domain points, we can build this entire covariance matrix, right? Then we can say that this function is a random sample from this normal distribution. And now that we know the values of certain dimensions from the training set, so this y can be seen as a probability distribution, a conditional probability distribution, given the p of y given x is already given, because from the training set we can give, then we can use this formula that we saw here, and then we can figure out this formula says p of x given y, but it also applies for p of y given x. X and y are interchangeable in that one. So we can just give a p of y given x. So we will get a probability distribution, a conditional probability distribution as an output of a Gaussian process inference task. Okay, this is probably confusing. We will see an example now. So let's say that we are talking about a regression analysis problem where we are trying to predict house prices. There are 4 features: area of the house, distance to the bus station, distance to the metro, and the number of grocery stores in the vicinity. Right? So we have 4 features and we try to predict the house price. We have 4 points for which we know the house price, and the 2 points for which we don't know the house price. We are seeking a prediction for them. right? Now, if we combine this 4 and 2, we get a system with 6 rows, of which 4 is known, 2 is unknown, and we have already seen this. Each row becomes a dimension, right? So, which means that there are 6 dimensions to it. It's basically a 6 dimensional vector. The house price can be seen as a 6 dimensional vector, which is a random sample from a probability distribution with a 6 cross 6 covariance matrix. And it cannot be any 6 cross 6 covariance matrix, right? Then it will be very strange. That covariance matrix must be tied to the domain. And what is the domain? That is the design matrix. We have got the 4 columns out there, right? The feature columns. That these are our domain points. And we'll take these domain points, 6 domain points, and we'll construct a 6 cross 6 covariance matrix in such a way that the covariance value of I comma j, which is like the ith domain point and the jth domain point, will be in such a way that if those two data points are close to each other in some sense of the similarity, right? Close to each other, which means that their function values are also similar, then they will have a very positive covariance, right? However, if those two data points are neutral, right, then they will have a neutral covariance and so on, right? We can build a covariance matrix that basically is based on the similarity of the domain points with respect to the function values. If we can design something like that, then this house price can be seen as a random sample from that distribution. That distribution is completely known now. We know the mean, which is taken as 0 usually, and the covariance matrix. We have both of this information, and we have 4 known points of that random sample. Now since we know all the 4 dimensions, the rest of the 2 can be taken as a conditional distribution from that distribution, from the known probability distribution, right? So we just condition that probability distribution, which again we get a Gaussian. There's an analytical formula for that. So you simply apply the formula, then you get a prediction for the unknown. The prediction set, the question marks here, will be returned as a 2 cross 2 joint probability distribution, right? So the output itself is a probability distribution. So yeah, that's what this slide also talks about. I don't have to go over it. All right. So, what are the applications of Gaussian processes? Gaussian processes are typically used for interpolation, right? And especially when the data is less. When the data is less and where every other method is not suitable enough, Gaussian process make an ideal choice. And given the fact that they give a probability distribution as its output, right? We can examine the variance of the probability distribution. And if that variance is too much, then we know that the point at which we are seeking a prediction is far away from the training set, right? Whereas if if the variance is somewhat less, then we know that we have got points closer to the a given point in the training set, and so we can be a bit more relaxed, right? So these are the major applications of GP, right? And this was also known by the name as a name of kriging in the geostatistics world. Some South African miner developed it separately, but Gaussian process, as we know it today, was developed by Rasmussen. He's a PhD candidate, and he must be a doctorate now. But he's the one who developed this Gaussian processes. And we also seen how sensitive the choice of covariance matrix is, because the covariance matrix should actually model the similarity between the domain points with respect to the function, right? If we happen to choose a covariance matrix which is not modeling it correct, you will still get outputs, but the outputs are wrong, right? So there is a need to tune and find the right covariance matrix, and this is central to Gaussian process. If you miss this, if this process is not done properly, you will get completely wrong results, right? So this is called as ARD, automatic relevance determination. This is nothing but you do your cross validation across a set of kernels, covariance functions, and their hyperparameters, right? You keep running this, and then you finally figure out what actually works well, right? Even if you select a covariance function or a covariance matrix by automatic relevance determination method, I strongly suggest go ahead and examine the covariance matrix for a given number of points and see for a given point what does the covariance matrix consider as closer to the given point, right? And then go and check in the data. Are these data points really close enough? If they are really close enough, then it means that the covariance matrix is modeling similarity between the domain points with respect to the function properly, right? And there are limitations to GP, like the analytical formula for finding the conditional distribution makes use of inverses, matrix inverses. And we all know that if the determinant of a matrix becomes zero, you cannot have an inverse for it, right? So degenerate inverses are a problem, numerical stability problems are there. Most of the times, the underlying library, the library which implements Gaussian processes, takes care of it. But as a practitioner, you should be aware of this. And it's not a very scalable method. We already saw that GPs shine well when there is less data and not when there are more data, because there are better methods when there is big data. So it's not scalable. And categorical variables are not natural to GP, but I'm sure modern libraries have some kind of support for categorical variables, some kind of support here and there. So if you're using categorical variables and if the underlying library is supporting, you probably need to investigate a bit. Again, look down the covariance matrix and look what it is considering as similar, what it is considering as dissimilar, and try to verify it in the data once to be sure that the categorical variables is handled, is not screwing up anything, right? And that brings us to the end of the slideshow, part one. In part two, I'll be going over a Jupyter notebook. I think a lot of exciting stuff was there in this Jupyter notebook. We'll talk about univariate discrete distributions, what is a joint distribution, and what kind of formulas we'll be using for Gaussian processes. And we'll be sampling functions as random samples, spiky functions, smooth functions, conditioned functions, all kinds of stuff. And we also do a regression problem by hand, right? A hand coded example of a Gaussian process. All this I'll cover in part two, which will come a week from now, right? So until then, stay tuned to my channel, subscribe, and see you soon.